Okay guys, this video is about two variable statistics. We typically refer to this as correlation and regression. And it's one of the cooler things I think to teach in a beginning statistics class. So let's get the ball rolling here. First thing, it's very important to point out to your students that you have to have two quantitative variables for correlation and regression. Categorical variables, there are statistical techniques out there that allow you to assess the strength and the relationship between two categorical variables. This is just not it. So we need two quantitative variables. The two components here are correlation. This is a descriptive statistics measurement where we create a scatter plot, which is a picture, and two measurements called the correlation coefficient and the coefficient of determination that give us think about they're kind of like means and standard deviations. These are numbers to just examine the strength and magnitude of the relationship between X and Y for the particular sample that we're given. We don't conduct any inference in Math 1500 for two variable statistics. Anyway guys, the second part is linear regression. This is where we fit a linear model to our data and ultimately examine something called residuals as well. Motivating example, what I have here, of course, if you've ever had me in class, you know I love sports. And what I've done here is I've collected some data on the length of time it takes to complete a game and the number of penalty yards. So for obvious reasons, I've let penalty yards be X and the time required to complete the game in hours be my Y. So first thing I would want you to do probably is, if you use this as an example in your class, is have your students enter the data in either their calculators or R. Now guys, there's going to be a follow-up video, and it'll actually be a pretty quick one, where I put these numbers in the calculator and in R and show you how to carry out the analysis. Okay, so let's go forward. Okay, so game plan, we're going to numerically and graphically describe each variable. Second, we're going to describe the relationship between penalty yards and length of game using a picture, the scatter plot, and R and R squared. We're going to fit the slope and intercept of our regression model. Helps us better describe the relationship, and it may be used also in terms of predicting the length of a future game from its penalty yards. And the final thing I want to do is examine the residuals, and what the residuals allow us to do is address the question, is a linear model appropriate for describing the relationship between X and Y? Alright guys, descriptives numerically describe each variable by reporting the mean, median, standard deviation, quartiles, IQR, and range, and graphically represent each variable by constructing a histogram and a box plot. Remember, histograms give distribution shapes, box plots look at outliers. So guys, jumping into the correlation part, if I look at a graph, which again I'll show you how to do on the calculator and on R, this scatter plot indicates clearly a positive relationship, and it indicates a moderate relationship. Strong relationships, if you can imagine a line through the central focus of your data, if there's not much variation away from the line, we have a strong relationship. If there's a little bit of variability, there's a moderate relationship. If there's a lot of variability, we call that a weak relationship. The positive and negative parts should be clear. The numbers. The correlation coefficient, which will always be between -1 and +1, here indicates a moderate and positive relationship. And the coefficient of determination tells us that 57.7% of the variance in Y can be explained by small changes in X. Okay. Correlation coefficient breakdown. These are not hard, fast rules. but it's it's the way I was taught, and it's a pretty good indication of the classification of the relationship: strong, weak, let's see, strong, weak, or moderate, and either positive or negative. So the sign of R tells us positive or negative. The magnitude, we look at the absolute value, producing either weak, moderate, or strong. Regression, when we fit our regression model, we see that the slope is 0.0093. This tells us as the penalty yards increases 1 yard, the predicted length of game increases 0.0093 hours. The intercept A is 2.32, and that's not the right intercept. Okay, so guys, I messed up here. The intercept is the value of y when x is equal to 0. So what we're going to say here is completely ignore the final bullet under intercept. What should go there is the interpretation of the intercept, which would say something to the effect when x is equal to 0. So when there are no penalty yards in a game, the predicted length of the game would be 2.32 hours. So make sure you make that change when providing the interpretation of the intercept to your students. I would say it's the first mistake I've ever made, but you know it's not. So guys, our model is y equal 2.32 plus 0.0093x, and I like for students to use the name of the variable instead of generic x's and y's. So we would say that the length of the game can be predicted by the model 2.32 plus 0.0093 times the number of penalty yards. So you'd want your students to be able to use this to predict future values. So let's say, for example, that we want to predict the length of the game when there was 100 penalty yards. And it looks like by inserting 100 in for penalty yards, we would have 3.25 hours. It's not appropriate, although it would be in an algebra class, to insert the length of the game and solve for the penalty yards. That's not what we're doing here. Regression models predict y from a particular level of x. So don't get caught up in that mistake. So guys, common mistake here. Predict the length of game when there was 150 penalty yards. The correct way is to insert 150 into your model to come up with 3.72. I want you to put this on your radar because a lot of students will go back to the original data set and look at the value for 150 and say that the predicted value is 4. So this is a really, really good way to point out the difference between an observed value, which is the 4 when x is equal to 150, and the predicted value of 150. It also leads very nicely into the interpretation and definition of a residual, which is exactly the difference between what was observed and what was predicted. Another common mistake in using a regression model is to think that you can put any value in for x. Now, if I ask my students to predict the length of game when there was 250 penalty yards, it's very tempting for them to put the 250 in and come up with a sort of a correct answer of 4.65. But guys, this is outside what we call our problem domain. This requires something called extrapolation, and extrapolation is not cool. So if we look at our values for x, the minimum value of x was 35. The maximum value for x was right around 200 at 196. Our model was created for values from 35 to 196. It's not appropriate for values outside this range. So don't let students do that. It's kind of like this. What if you went into a first grade school, a group of first graders, and you create a model, and whatever it may be. Would you feel comfortable taking that model into a nursing home and using that model on people in their 70s, 80s, 90s? The answer is no. The model wasn't created for the population of nursing home residents. It was created for first grade students. So, don't use your model exhaustively. There are restrictions on the values we can put into our model and the population that we can use our model on. For example, I wouldn't feel comfortable here. This is for football games. I wouldn't feel comfortable using this for a soccer game. It wasn't built for that reason. All right, guys, residuals. Now, residuals are extremely important. At the big boy, big girl level, we call these errors. But at the end of the day, the residual is nothing more than the observed y minus the predicted y. So in this situation, the residual would be the observed length of game minus the predicted length of game. And the reason, the sole purpose of examining residuals, and I'm not going to say the sole purpose, but the most important purpose, at least in my opinion, of examining residuals at this level is to determine if a linear model is indeed appropriate for describing the relationship between x and y. Now, let me show you how this works. Sometimes when we look at the relationship between x and y, it's obviously clear that a linear model is appropriate. And this is a situation where a straight line fits our model well, no brainer. A linear model is appropriate. Sometimes it's obvious that it's not. You can see where I fit this data with a curved red line. A linear model would not fit this data well at all. But in the real world, it's not always as obvious as these two cases. So what I would want you to do here is, first of all, dive into residuals and calculate a couple by hand. That way students don't just become a robot to their calculator or R in terms of calculating the residuals. So for example, if I want to get the residual for the first game, you can see there was 196 yards. The Y was 4.2. So the observed Y was 4.2. I can put 196 into my model to get a predicted Y of 4.14. Once we get the observed and the predicted values for Y, the residual is very easy to find. It's just a subtraction. So the interpretation here, again, you can probably tell by now that at the 1500 level, I'm all about interpretations. Make it easy on students to find the numbers. Force them to put into words what the numbers mean in telling a story about whatever the measurements represent. So I would say this game lasted 0.06 hours, about 3.6 minutes longer than we would have predicted based on its number of penalty yards. So the observed was bigger than the predicted, so the game lasted longer than we would have predicted. Guys, residual plots. The residual plot on the left is what I call random. Now it's got a little bit of fanning out. So there's a little issue here. I probably wouldn't go into this with my 1500 level students, but there's a little issue on one of the assumptions that we have equal variances across levels of our X, because you can tell at the 20 level there's not much variation, whereas at the 50 level of temperature there is a lot of variation. Nevertheless, what I want you to focus on with your students is, does your residual plot, your residuals over your original X, does it look random or does it look like a U-shaped? Random tells us that a linear model is appropriate. A U-shape tells us that a linear model is not appropriate. If I look at the residual plot for these measurements, I clearly don't have a U-shaped. What I have is random scatter plot. So we would conclude that a linear model is appropriate for describing the relationship between the number of penalty yards and the length of time for the game. So guys, getting ready for the final project. You want your students not only to be able to find the numbers, use their calculator or R to find the numbers. You want them to write it up appropriately. So what I've done here is I've given you an example of how I would write this up at the 1500 level. Now, you know, if I were doing something like this, you know, I would conduct inference. But that's not what we do in the 1500 level. The 1500 level for the two variable statistics, we just hope that they can statistically describe the relationship. Okay? So guys, that's the end of this. What I'm going to do next is enter the data into both the graphing calculator and R and demonstrate both ways of finding you know, the slope, the intercept, R squared, and so on and so forth. Okay guys, going to be a lot going on here, and I just hope my computer can, the processor can handle all this stuff. I've got the TI-84 on the right, obviously, and I've got this motivating example from the video that I just completed. What I want to do is run through this very quickly and show a complete illustration here. So guys, first thing I'd want to do is hit my stat button, go to edit. And what I want to do now is I want to go up and clear each list. So guys, if I'll hit clear, enter, that'll get rid of the numbers and not the list. So hit clear, enter, and go up to L3, and I want to clear that out for reasons that'll become clear in just a second. So guys, the very first thing that I need to do is type my data in very carefully. It's really frustrating for you and for students if you you know, start running your analysis and you get different. I should have already had this done, to be honest with you. But I don't, so anyway, if you're playing along, that'll give you a chance to. Too bad I can't sing. That would be scary. Okay, this is boring. Alright, let's make sure everything goes together here. 4.2. I could have had some music or something going. 4.1. 3.5. 3.2. 3.2. 3.6. Would have been fun if we had a data set of about 50. 4. 3.1. Come on, come on, come on. And 1.9. Yeah, guys, as I said in the video, the first thing I'd want to do is look at these lists independent of each other. So I would first of all want to describe penalty yards. So the first thing I'd want to do is look at a picture. So I'll go up to stat plot. Guys, make sure that all of your plots are off initially. So you can just hit the number 4 and hit enter, and that'll turn all the plots off. If you have multiple plots on, you can get errors, which can be very, very, very frustrating. So the first thing I want to do is I want to turn this on, and I want to look at a histogram for just penalty yards. So I have L1, which is cool. So now I'm going to go zoom 9, and I get some stuff. Now let me explain what's going on here. I taught a linear programming class this summer where we did some shading, and so I've got some stuff here that I need to get rid of. Alright, Now let's go back to graph and we'll get kind of a weird histogram. I don't know how you'd explain that. Next thing I want to do is look at a box plot. Guys, you got to scroll all the way over. Don't forget to select it. And go zoom 9. And you'll see we have no outliers. While I'm at it, while I'm on a roll, I'm going to look at a histogram for length of game. Guys, instead of L1, I need L2, so I'll hit second function 2. Now, I got to go back up before I go zoom 9. And, you know, bell-shaped and symmetric, that's cool. Let's take a look at the box plot to see if we have outliers. And it looks like we don't have outliers. Got a little tail there, indicating a little bit of skewness, but it's all good. All right, guys, next thing I'd want to do is I'd want to look at the descriptives. So I'd come over to Calc and do one variable stats. And I want to do this first of all for X, which is the number of penalty yards. So hit calculate. And we can see that the average number of penalty yards for these 10 games, these 9 games is 118 yards. The standard deviation is 57.29. And the 5-number summary we see is provided at the bottom of the screen. Now, we'd probably want to be able to give the IQR. It's not given. Well, yeah, this is one thing I don't like about, I forget what it was. But anyway, guys, when you go away from the screen, make sure you write down Q3 and Q1, or at least remember them. Guys, statistics, let's go to one variable stats again. What I'd like to be able to do here is look at the descriptive statistics for the time to complete the game. So come down to calculate. So for these 9 games, the average length of time was 3.42 hours. Standard deviation 0.70. And of course we could scroll down and get the 5-number summary. So if I want the IQR, I need to take 4.05 minus 3.15. Now, most of us can do that in our head, but guys, I promise you, some of your students won't be able to. Or at least some of my students won't be able to. So guys, we got 0.9 as the IQR. And we could find the range by taking the high minus low, or max minus min, and do the same. Okay, now once we're done with examining the descriptive or presenting the descriptive statistics for the variables separately, now we want to jump in and look at the relationship between the two. So the first thing I'd want to do is create a picture. So I come down to the scatter plot, and I need my X to be L1. I need my Y to be L2. Now guys, I need to scroll back up before I hit zoom 9. And I get the scatter plot that I showed you earlier. So guys, clearly we have a positive relationship, and I would classify this as a moderate relationship. The next thing I want to do is I want to get into finding 4 things. I want to find R, R squared, the slope, and the intercept. There's a really easy way to find them all on one screen. If you go to test, you can go all the way down to linear regression t-test. Put L1 and L2 in. Now guys, I'm going to show you something here. Where you see REGEQ, regression equation, I want you to do the following. I want you to have your students do this. I want you to go to variables, and I want you to go over to Y variables, and I want you to hit function, and I want you to select Y1. Now what that's going to do when we run our regression, when we run R squared, well, we run the linear regression t-test. Let me back up a little bit. A lot of people give me a hard time about this. They're like, there's another way to do this. You can do the linear regression AX plus B or A plus BX back under calc. I like to use this because some students might get to a point to where they actually do conduct inference for a regression. This takes care of that. So in addition to this Y1 that I put in, which will graph the linear regression model on our scatter plot, I get the following. Now, if I scroll all the way down, I get my R and my R squared. Notice my R is 0.76. The R squared is always presented as a percentage, 57.7%. And if I scroll back up, I get my A and my B. You can see by the form up here that A is the intercept and B is the slope. So 2.32 and 0.0093 correspond to the value for the intercept and slope that I gave you earlier. Now, since I put the Y1 in for my regression equation, I can go to graph, and you can now see that I have my model on the scatter plot. Now, for example, I asked you in the video earlier, let's predict when x is 100. So if I go second function calc and go to value, I can type 100 and hit enter. It will give me the predicted value. So a game that has 100 penalty yards is going to predicted, or the predicted length of the game is 3.25. Easy for you to say, right? Now, the reason I like this on the calculator is because if I try to do something goofy and predict for a value that's outside the problem domain, such as 250, it'll give me this screen. It'll give me this screen and tell me, you can't do that. It's outside the problem domain. So this actually keeps you honest. Now, guys, let's quit and get out of that. What I'd now like to do is create my residuals. And if you follow the instructions that I've given you here, in that you've gone to stat, you've gone over to test, and you've gone down to linear regression t-test, and you've run that. If you've done everything that I've done, if you go second function list, somewhere down here around, it could be 3, 4, 6, or whatever, somewhere down in that list, you're going to see RESID. Your calculator has already calculated the residuals. So if I take those, I can store the residuals in a list so I can examine them. Well, the reason I cleared out list 3 early on before I started is I want to take my residuals and store them there so I can see them. Okay? So gang, if I go to stat and go to edit, in L1 and L2 I have my X and my Y respectively, and L3 I have my residual. So the residual for the first is 0.0505, telling us that the observed length of game is 0.0505 hours longer than the predicted length of the game based on the number of penalty yards. Now, another thing that's important for us to be able to do is to be able to create a scatter plot of the residuals over our original X. Well, I've got the I've got the scatter plot selected. I want the residuals over the original X, so I'll leave L1 there. And guys, I stored these things in L3 for multiple reasons. I want to be able to access them from my list. Guys, go all the way back up to the top, go zoom 9, and you'll see that we get kind of a random scatter plot indicating that a linear model is appropriate for describing the relationship between X and Y. All right? Now guys, let me show you how we would do this on R. So I'm going to close down that, and I'm going to go into R, and I'm going to go split screen until I get my data entered. Alright, so the first thing, I'm just going to call this X, and I'm going to use the C function. Hopefully I don't make a typo, but if I do, it's all good. And I'm just going to call the other Y. Alright, so if I want to do a histogram of X, I can get it. Notice it looks a little bit different. The selection of bins is a little different in R than it is your graphing calculator. If I want to do a box plot, I just go box plot. Clearly I could do a histogram of Y and a box plot of Y just as well. If I want to do descriptive statistics, I can do summary X, and this is going to give me my mean, median, and the quartiles. If I want to do the IQR, that's not going to work. It's got to be capital. I always forget that. It's going to be 86 if I want the standard deviation, and if I want the variance, I can get VAR of X. Clearly, I can get the descriptive statistics for Y as well. But guys, the purpose here, what I really want to be able to do is I want to be able to look at my model and create residuals. So first thing I want to do, and I'm just going to call this model, and I'm going to use LM, and I want to predict Y from X. So that's going to be Y tilde X. Guys, if I just type model, I now see that I get the same the same slope and intercept that I did with my calculator. To get R, I just do correlation X comma Y, and obviously to get correlation squared, which would be R squared, I would go correlation X comma Y quantity squared. So 57.7% will be my R squared, and 0.76 is my correlation. So this is much quicker, I think much more seamless than the graphing calculator to come up with these values. Turns out the residuals are as well. If I just take the residuals of my model, very quickly I get the same values I got that I stored in L3. Now, for reasons I'll show in just a second, sometimes it's nice to store your residuals as something, and I'm going to call them RES. For example, now, if I want to do a scatter plot of my residuals over my original X, and you can see that I get the plot that I need. Sometimes it's nice to know the standard deviation of your residuals. So it's 0.45. Also, you should always point out to your students that the mean of the residuals will always be 0. And it'll kind of freak them out a little bit. Why doesn't it come out to just be 0? Well, e to the negative 17 is trying its hardest to show 0. The predicted values, I'm sorry, the predicted values are easy to get. So just do fitted. So the predicted values are given here. Now sometimes I think it's nice to have a table that shows everything. So I can do data frame. I can go X, Y, predicted, and residuals. And what I get here is I get a data frame. I get my X's of 196. I get my Y of 4.2. The predicted value is 4.149, call it. And the residual is 0.0505. So we get the observed Y, the predicted Y, and then the difference in the observed Y and predicted Y, which we call the residual. All right, guys, so all I got. Have a good one.